Hello again, guys. Welcome to part 2 of lecture 6 of our lecture series, Chemistry for Engineers. And as you already know, our topic is on quantum chemistry of atoms. So this is basically where we last left off. So today we will be focusing on the quantum mechanical model as it relates to atom. It's not going to be as detailed and as complex as it really is. With the invention of quantum mechanical model, we were also able to better describe chemical bonding more accurately. It allowed us to design materials, to improve on the design of our materials. In the quantum mechanical model, electrons are not viewed as particle, but they are viewed as wave or delocalized through a region of space called orbital or in a cloud of probability. It is important to add that the location of electrons in atoms is defined by a set of 4 quantum numbers. So we will be looking at quantum numbers, Schrodinger's equation, which basically looks at the probability of finding the electron in this cloud of probability orbiting the nucleus. And we'll also be correlating this with electron configuration. So as we said before, the location and energy in an atom is defined by a set of 4 quantum numbers. These quantum numbers are described in what we call the atomic orbital. There are S, F, P, D with different shapes, and the shapes are basically the region where the electron can be. So we have the principal quantum number, the angular momentum quantum number, which is L, the magnetic quantum number, which is ML, and the magnetic spin designated MS. The principal quantum number is an integer that we've met before, designated N. These basically represent the energy levels in which the electron in a given orbital have the ability to exert. So as we said before, N1 would basically be the lowest energy level, followed by N2, N3, N4. The angular momentum number is L, which describes the shape of each orbital. If an electron has n value of 1, then L would be 0, because this is the first orbital where S is spherical. So when L is 0, we're describing the S orbital. When L is 1, we're describing the p orbital. When L is 2, we're describing the d orbital. L3, F orbital. So S orbital is spherical, p orbital shapes like a dumbbell or 8. The lobes for the p orbitals extend out on 3 axes. The lobe for the d orbital contains 5 of these per energy level, while the F orbital consists of 7 per energy level. The magnetic quantum number, or M sublevel L, this has a value of negative L or positive L. So when L equals 2, M sublevel L would be equal to -2, -1, 0, 1, 2. The electron spin can either be plus half or minus half. So no single atom will have the same quantum number as stated by Pauli exclusion criteria. Even 2 electrons in the same orbital will have opposite spin. So the magnetic quantum number describes how many orbitals there are at a given type of energy levels. The Schrodinger's equation, as confusing as it looks, basically is trying to tell you everything about the quantum system, meaning the potential and kinetic energy of the electron, as well as the probability of finding the electron in a given location around or within each orbital. So in a nutshell, it tells you about velocity, kinetic energy, potential energy, and the probability of finding the electron somewhere in time and space within a given orbital. There are different versions of the equation, time dependent, time independent. So basically the energy of the system is the kinetic energy plus the potential energy. So you're trying to find the energy of the electron within the system. And of course, the energy will determine the movement or a location in a given space in time. So at some point, if you're confused, just remember that Schrodinger didn't understand his own equation. Here we have have energy times psi. Psi stands for the wave function, or where the electron is likely to be, but not will be. So here we have energy. Energy is equal to Planck's constant times frequency, which we already know. And the rest of the equation is basically potential energy plus kinetic energy, which basically gives the total energy. So recall that the kinetic energy is the energy while an object is moving. The potential energy is the stored energy that depends on the relative position of a system. So you're basically trying to find the potential energy and the kinetic energy of the wave function. So there are different solutions to the kinetic and potential energy, where psi is equal to the square root of 2 divided by L cos times the square root n times L when n1, n3, n5 is odd, or psi times x, which would be equal to the square root of 2 divided by L cos sine times pi n times x divided by L when n, 2, 4, 6 is even. Most of the variables in the equation are either constant or a value that you probably already know. So combining both solutions, you basically end up with E equals Planck's constant square n square pi square divided by 2m for mass L square. Everything is a constant or a whole number. H pi is a constant, 2 is a constant as well. M stands for the mass of the electron, which is also constant. Pi is a constant. L is the length of the box, which is also constant. And N, as you already know, is the different states of the electron at different energy levels. So basically, the energy can only have certain values. So this first equation looks at psi, or the wave function, when the electron is in the first energy state, which means that n is equal to 1. So if you square this equation, you get the probability distribution, or where the electron is likely to be. So here we can see the different orbitals at a given location in space. So here you see the areas that are highly dense represent the probability of finding the electron in a given space. Or between each orbitals, you have nodes. So the nodes are points or planes where you won't find the electron. As the energy level increases, the electrons are located further away from the nucleus. So the orbitals get bigger. So the order in size is 1s, 2s, 3s. And again, in the quantum mechanical model, the electron comes in the form of waves and can be located at a given space around the nucleus. The first evidence of the wave nature of electron came through diffraction experiment in 1927. Diffraction was already a well understood phenomenon of waves. So the observation of electron diffraction strongly suggests the need for a wave-based treatment of electrons. So here we have a laser where a photocathode produces a radio frequency field which passes through a magnetic lens that produces an electron beam, which would cause a diffraction pattern in the electron. A mathematical description of wave generally begins with a function that describes the periodic behavior. Such a function is referred to as a wave function. The simplest function can be used to describe the simple oscillatory motion. Although the function that describe electron waves tend to be more complicated, the idea is the same. The notion of using mathematics of waves to treat electron was first put together by Erwin Schrodinger, so it's called the Schrodinger's equation. So a simplified version of the Schrodinger's equation includes the Hamiltonian operator, or energy operator, times psi equals energy times psi. So the Hamiltonian operator links the total energy, the potential, as well as the kinetic energy. The H term is an operator which designates a complicated series of mathematical operations to be carried out. E is the energy, and the symbol is basically the Greek letter for psi and is a wave function for the electron. If we write out the entire operator H, we would find that Schrodinger's equation is actually a second order differential equation. In most cases, the equation cannot be solved exactly. So the study of quantum mechanics invariably involves approximation. So this is basically the Hamiltonian operator H for hydrogen atom. For it's a sum of kinetic and potential energy. The concept of the wave function is in particular is central to the quantum mechanical model of atom. The wave function function contains all the information we can ever know about the electron, if we can determine the means by which to extract the information. So the Schrodinger's wave or the psi function tells us the probability that the particle is at a position X. The purpose of this equation is to describe the total energy of the electron as it moves through the three-dimensional space surrounding the atom's nucleus. Because the nucleus is the center of the atom, it makes sense to define this as the origin of our XYZ coordinate system. Here we have the X towards you, Z here, and Y is depicted here. We would assume a basic point here, which would represent the nucleus. And here we can see p orbitals associated with the XYZ coordinates. And remember that we said that we had the sp df orbitals. So unlike the s orbital being spherical, the p orbitals point in a specific direction. They're mutually at right angles to each other. So they're arbitrarily given px, py, pz by convenience based on their specific direction, because as the xyz changes, they change their direction or tumble around in space. All energy levels except the first energy level have p orbitals. We might expect that there should be terms for the kinetic energy and for potential energy, and in fact there are. So the xyz terms account for the potential energy, which is a function of position. The other term on the left side accounts for the kinetic energy. So the Schrodinger's equation expresses the total energy as the sum of kinetic energy and the potential energy. So basically, the electron can move clockwise, anti-clockwise while emitting potential or kinetic energy while existing in waveform around the nucleus. So here we can see all the orbitals again. We said you have the s orbital, the p orbital, d orbital, as well as f orbital. S orbital is entirely spherical. It is closest to the nucleus and can only admit 2 electrons. And eventually you'll see that the movement of each electron will have to be opposite, as in clockwise versus anti-clockwise. The p orbitals we basically just looked at. So at the third level, you have a set of 5d orbitals. At the fourth and higher level, you have 7 f orbital. So the easiest way to understand the orbitals would be to consider the energy level of the atom. So say for example, here we have nucleus. Here we have N1. Here we have the second energy level, which is N2. Here we have N3. And here we have the S, the P, D subshell. So the S subshell, and we have what is called the angular momentum and the maximum electron. So we basically will see how many electrons or the maximum electrons that can be occupied in each subshell. So we already know the subshells are S, P, D, as well as F. And the angular momentum describes the shape of the sublevel. So we can say this is 0, P is 1, D is 2, F is 3. So the maximum electron is 2, maximum electron is 6 for P, the maximum electron for D is 10, this is 14. So this is N1, this is N2, this is N3, N4. Out of chaos comes order. So this is the configuration of the subshell. S basically is 1. So you can basically have a 1S, a 2S as well, or a 2P, or you can have 3S, 3P, 3D, or 4S, 4P, 4D, or F. So 0 to positive 3, 0 to negative speaks with the direction of the electron. So it can be clockwise or anti-clockwise. The Schrodinger's equation describes the energy of electron as for any object or particle. The total energy includes both kinetic energy and potential potential energy. But the potential energy is the most important in describing the structure of the atoms. The potential energy of the equation is associated with the Coulombic attraction between the positively charged nucleus and the negatively charged electron, as well as the repulsion between charged electrons. So here we have kinetic energy, and here we have the potential energy. E for energy times psi divided by Planck's constant squared. Here describes the mass that is relative to the process. Planck's constant, which is equal h2 pi, divided by the mass that is related or relative to the process. The psi is also known as a Schrodinger's wave function. Distance squared times Schrodinger's wave function divided by the distance squared plus the potential energy. So the periodic nature of waves allow many solutions to the wave equation for many given potential interaction. Schrodinger's equation is often written as this, is a simplified version where the Hamiltonian operator times the Schrodinger's wave function, which is equal to the energy relative to the Schrodinger's wave function. Planck's constant, the mass in the relative process. So this is the quantity that describes how the wave function changes from one moment to another as the future unfolds, because remember that it's basically projecting or giving a probability as to the location in time. The process is squared, presenting a dynamic geometry, and if it is reformulated as linear vector, psi in time less than each new vector is formed by adding the two previous vectors together. So v is basically the velocity which describes the forces acting on the particle, and I is basically the square root of -1, and this describes how psi changes over time. So we basically will only be interpreting this equation and not calculating anything from this equation, because it does not automatically lead to accurate identification of the probability. So basically what's happening in the Schrodinger's equation is the quantum state psi is changing with time and is dependent on the total energy in the spectrum. So it's basically dependent on the kinetic energy as well as the potential energy. The equation will only allow you to predict how a quantum system should behave, which is why you basically have a mathematical model for all the energy states within the system. So you're basically calculating the energy states of the electron moving from different energy states. The potential as well as the kinetic energy gives a determination as to where or what location to predict the wave or the peak of the wave. Calculations are usually computer generated, and even the fastest computers usually can't process the information due to computers today not being fast enough to generate long enough data or enough data for all the activities in and around the system. So the system would be all the energy state or all the electrons in the lowest energy level. So you would have to consider the kinetic energy of the first electron, the second electron, electrostatic activity between the electrons as well, activities within the nucleus, the proton. So in essence, we are nowhere near having a logical or realistic calculation in terms of data due to various constraints. The simplified version of the equation basically factors the Hamiltonian operator psi or the Schrodinger's operator, where n is an index that labels the different solutions. So whatever it is labeled, and this is equal to energy times energy of the solutions times psi. So the wave function times the solution that provides a solution to the equation for an atom can be written in terms of two components. So you have a radial component and an angular component. The radial component is depending only on the distance of the electron from the nucleus. This component factors the radius of the nucleus. It factors the distance of the electron from the nucleus, and the angular component is dependent on the direction or the orientation of the electron with respect to the nucleus. An orbital is the quantum mechanical equivalent of the location of an electron, but because we are treating the electron as wave, this location is actually a region region of space, so rather than a particular point. The names of orbitals, as we've discussed before, can be S1, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, as we've written before. And again, we spoke about 4 quantum numbers: the principal quantum number, which is designated N; the secondary quantum number, which is designated L, looks at the shape of the orbital; the magnetic quantum number, which is designated ML; and MS for the spin or the magnetic spin. So we spoke about the secondary quantum numbers, which specifies the subshells. When N is 1, the only possible value of L is 0. So there's only one subshell. This basically means that we're dealing with the s orbital. So in the s orbital, N can be 1, 2, 3, 4, all the way up to 7 or more if necessary. But always remember that L has to be 0 while M has to be 0 as well. When N is 2 or more, L is 1. So this basically means that there are 2 subshells, both S and P orbital. And remember that the magnetic quantum number is either equal to 0 or plus or minus 1. When N is 3 or greater, the angular momentum number, or L, is 2, which basically means that the magnetic quantum number is either 0, plus or minus 1, or plus or minus 2. And this would be the d orbital. When N is 4, the angular momentum number is 3, where M is 0, plus 1, plus 2, plus 3, or minus 1, 2, or 3. And we're basically dealing with the F subshell. So again, the subshell can either be S, P, D, F. And the coordinates are X, Y, Z. The s orbital is spherical, p orbital shapes like a dumbbell or 8, d orbital is like a clover leaf, f orbital is pretty confusing, but it's basically a stack of clover leaf, dumbbell. P orbital lobes extend out on 3 axes. D orbital lobes extends out on 5 axes per energy level, while the f orbital lobes extend out on 7 axes per energy levels. And this is basically repetition. The angular momentum number is L, can be 0, 1, 2, 3. So we have the primary quantum number, which is designated N1, N2, N3, N4. It's an integer that can only be a positive number. The angular momentum number describes the shape, the different configuration of the orbitals. When N is 1, angular number is 0. When N is 2 or greater, the angular number is 1. When N is 3 or greater, the angular number is 2. When N is 4 or greater, the angular number is 3. And the subshell, as we know, are S, P, D, F. And of course, if we miraculously engineer a few new atoms or see that there is more out there in the universe that we assume, then we can exist this subshell to different orbitals. So as it relates to the magnetic quantum number, the emission line split into 3, 5, or 7 components, as we've mentioned before. This observation points to the need for a third quantum number. This index, called the magnetic quantum number, is labeled ML and is an integer. It may be either positive or negative, and its absolute value must be less than or equal to the value of L for that orbital. Thus, when L is 0, ML is also 0. When L is 1, ML may be minus 1, 0, or plus 1. When ML, or the magnetic quantum number, is 2, ML may be negative 2, negative 1, 0, plus 1, or plus 2. So the magnetic quantum number indicates orientation of orbitals. So this is basically an example of a p subshell split into 3 orbitals, p, z, x, and y, as well as the number of the orbital within the subshell. If we count the total number of orbitals in each shell, it is equal to the square of the principal quantum number n square. So as we said before, where the value is 1, the value of L is 0. L is the angular momentum quantum number. The value of ML, or the magnetic quantum number, would be 0, and the number of orbitals would be 1. Where N is 2, the angular momentum quantum number is either 0 in the S subshell or 1 in the P subshell. And the value for the magnetic quantum number is either -1, 0, or 1. And the number of orbital would be 1 as well, or 3 for the P subshell. Where N is 3, the angular momentum quantum number, or the shape, is either S, spherical, which would be 0, or P, which is 1, like a dumbbell, or D, like a clover leaf, which is 2. So 0, 1, 2, S, P, D. And the magnetic quantum number is either -1 or 1, which we already know. The number of orbitals would be 3. For subshell D, the magnetic quantum number is either -1, -2, 0, 1, or 2. And the number of orbitals in this case would be 5. For the value of N, the angular momentum number can be either 0, 1, 2, 3, or S, P, D, F. And in this case, the value would increase up to 3. And of course, the number of orbitals we would have up to 7. So table 6.3 lists the actual wave function of the first few orbital of a hydrogen atom. Because we expect the atom to be spherical, it is customary to write the functions in spherical polar coordinates, with the nucleus of the atom located at the origin. Polar coordinates. The wave function of N is 1, and N is equal to shells of hydrogen atoms are listed. So a point in a three-dimensional space require an X, Y, Z coordinate. Here we have a Cartesian coordinate that you would naturally will have to convert to a spherical coordinate because the electron is contained within a sphere, where R would be the distance from the origin of the electron. This would be the azimuth angle we call phi in the XYZ plane. Then we have the vertical angle Z, which would be the position of the electron. Here we have the angle theta. This is also basically showing the XYZ coordinate in d orbitals, just showing the orbitals in different shapes, d orbitals in different shapes along the XYZ coordinates, where in this case R is the square root of XYZ. If we wish to have 100% probability of finding an electron, the amount of space needed is quite large and accordingly fails to provide insight about the tendency of the electron to be involved in chemical bonding. Conventionally, the space within which there is a 90% probability of finding an electron is chosen as a boundary for depicting orbitals. Within this convention, a plot of the angle part of the wave function will show us the shape of the corresponding orbital. Pictures of prototype sp and d orbitals are shown here. So the shapes of, from the left to the right, 2s, 2p, 3d orbitals are shown. So these basically are the images. Even though they look like pictures, they are plotted by obtaining wave function, and the different colors in shade indicate region in which the wave function has opposite signs. The s orbital is spherical, as we said before, whereas p orbital has 2 lobes and d orbitals have 4 lobes. The 2 lobes of p orbitals are separated by a plane in which there is no probability of finding an electron. The plane is called a node or a nodal plane. So here we have the nodes of the s orbital, and the lobes of the p orbital are separated by a plane in which there is no probability of finding an electron, which would be somewhere around here. The d orbitals has 2 nodes. These nodes give rise to one of the more intriguing philosophical question of science: if the electron can be either side of the node. but never in the nodal plane, how does it get from one side to the other? We can suggest an answer to this question in two ways. One is to remember that the electron behaves as a wave, and even classical wave motion, such as in string of a guitar, can have nodes. So here we have the 1s orbital with no node. 1s orbitals has no node. 2s orbitals has one node. 3s orbital has 3 nodes. So the cross-sectional view of 1s, 2s, and 3s orbitals are shown in this type of figure. The density of dots indicate the probability of finding an electron. The greatest electron density will be found in those areas that appear darkest. The white region within 2s, 3s are nodes. So no nodes for 1s, one node for 2s, and 2 nodes for 3s orbitals. So the d orbitals have radial as well as angular nodes. And here we have the nodal planes between the x, y, z coordinates. So d orbitals have radial as well as angular nodes, and these nodes are found between the x, y, z coordinates as nodal planes. So the d orbitals have 2 nodes, and the electron can be on either side. So if the electron can only be on either side of the node, but never in the nodal plane, how does it get from one side to the next? So the first thing is electrons behave like wave, and the second thing leads us to the uncertainty principle. This concept, stated by Heisenberg, expressed the difficulty of obtaining an electron. Simply put, uncertainty principle says it's impossible to determine both the position and momentum of an electron simultaneously and with complete accuracy. The uncertainty principle imposes a fundamental limit on observing the microscopic world and forces us to accept the idea that orbitals provide nothing more than probability of finding an electron. So this figure shows a cross section of 3 different s orbitals. I think we mentioned those before, corresponding to the principal quantum number n, 1, 2, and 3. So the nodes are in the radial portion of the wave function, as they are in many of the angular functions. So the nodes are in the radial portion of the wave function, just as there are in many of the angular functions p, d, and f orbitals. So the greatest electron density will be found in the areas that appear darkest. The white region within the 2s, 3s orbital represent nodes. So you basically won't find the electrons within the node. So for orbital radial nodes, there is one less node than the value of the quantum number. Thus, there is one node in 2s orbital, 2 in 3s orbital, and so on. So p and d orbitals, such as 3p, 4p, and 4d, also have radial nodes. So this basically shows a picture of orbitals in the N3 shell. The electron density plots for 3s, 3p, and 3d orbital here shows the nodes in each orbital. So 3s orbital has 2 spherical nodes. 3p orbital has 1 planar node on the right and a second hyperbolic node on the left. 3d orbital has 2 planar nodes. So the nodes along the plane or along the coordinates, or the nodes along the nodal plane. So this also shows the 3p orbital, where we have the radial node outlined here, angular node where the darker region shows increased density, which means that there's the likelihood of finding the electron between these nodes. So the nodes are between here and here. The nodes are between here and here. The nodes are between here and here. The concept of orbital shapes and energy ultimately provide ways to predict chemical reactivities and optimize conditions in which reactions occur. Halogen lamps are predicted on the chemical reaction of of halogen molecule with tungsten wire of the lamp, the role of halogen is depicted here. So traces of halogen gas here, iodine allowed to evaporate tungsten atom to return to the surface of the bulb filament. So these are the iodine atoms as well as the tungsten here, effectively recycling the metal atoms. So the tungsten are being recycled. This allowed the filament to operate at high temperature without compromising bulb life, and explain why halogen lamps are brighter than regular incandescent bulbs. The chemistry involved is actually much more complicated than shown here. So this is basically the tungsten filament, and the tungsten evaporate from the filament, which encountered the halogen atom, which is the iodine. The tungsten halide, or the tungsten and the iodine, migrate back to the filament and dissociate, replenishing the tungsten and the halogen. So it's basically a constant cycle of tungsten iodine, tungsten halogen, which would ultimately increases the longevity of tungsten or this type of light. In a normal incandescent bulb, the choice of filament temperature involve a trade-off between the brightness and lifetime of the lamp. Higher temperatures give brighter light but lead to shorter lifetimes because metal atoms evaporate faster from the filament. If halogen gas is present in the bulb, it can react with the tungsten as it vaporizes for the high temperature filament. If you include a gas or a halogen to interact with the metal, then it will increase the longevity. Again, showing the photoelectric effect, or the photon being emitted from the electron in the form of light. And we should imagine that at the level of the orbital, this is communication or interaction between electrons from different orbitals. And this is how we relate the orbital to electron configuration as well as light production. The resulting molecule redeposits on the wire, recycling tungsten. So for the production of light, when you combine the halogen gas along with the tungsten wire, the resulting molecule redeposits on the wire, recycling tungsten. So it basically recycles the tungsten atoms, and these cycle reaction allow higher operating temperatures and a brighter light without compromising on the lifetime of the bulb. We must therefore know more about the way the electrons occupy orbitals in atoms such as the halogen. So these are a list of the halogens: fluorine, chromine, bromine, iodine, astatine, tennessee. These are also their atomic number: 9, 7, 35, 53, 85, and the electron configurations are written here. So the important thing about the electron configuration is that the valence electron will decide how the atom will interact with other atoms, or the molecules will basically interact with other molecules. Remember that we're dealing with the photoelectric effect as well as the electron affinity as well, because these electrons will have to move from a higher energy level to a lower energy state, and also as well as emit electrons. So one could assume that the valence electron, or the electron on the outermost shell, will contribute to electron affinity, meaning that the electron will be emitted or released from the atom. So we would basically look at the valent electron. So if we look at the electron configuration for fluorine, chlorine, bromine, iodine, as well as astatine, we can see that the valence electron consists of the same configuration number. So the p subshell on all these electrons consists of 5 electrons. So let's see how we derive the electron configuration for fluorine, because this is helium 2 plus 2, 2p5. So fluorine has an atomic number of 9. So if we look at the subshell, N1 would be the S subshell, which would only contain 2 electrons. N2 can contain S subshell as well as a P subshell, and P subshell can occupy up to 6 electrons, and we have the number of electrons would give us the atomic number. So we have 2, 4, 6. So this would basically give us around 10 already. So for fluorine, the electron configuration would be 1s2. So we have 2 electrons in the s subshell. We'd also have 2 s2. At the second energy level, we would have 2, and the s orbital would contain 2 electrons. So that would be 2 and 2. So we already have 4 electrons. Remember that we have up to 9 for fluorine. So 2p, and if we have 4 already and we need 9, then p would contain only 5. And this is basically the electron configuration for fluorine. This is the abbreviated version because the electron configuration for helium is 1s2. So you could write helium as well as 2s2, 2p5, which we basically have here. And if we want to look for the electron configuration, for example, of chlorine, we would have to consider that the N3 energy level consists of S subshell, which we know contains 2, P subshell, which we know contains up to 6 electron or holds up to 6 electron. So here we will have the D subshell can hold up to 10 electrons. Let me just separate this from here so it's a little easier to understand. So this is fluorine. Here we have chlorine. So the atomic number for chlorine is 17. We have 1s2, 2s2, 2p6. After 2p, we have 3s. So 3s can hold up to 2. So we have how much so far? We have 2, 4. We have 10, 12 so far. And after 3s, we have 3p. So 3p, if we already have 12, we would basically only need 5. The abbreviated version is neon 3s2, 3p5, or 1s2, 2s2, 2p6, 3s2, 3p5. And you can imagine the same thing with the other elements. You have the atomic number, and all you need to know is that where n is equal to 1, the s orbital is possible with only 2 electrons being accepted or allowed in the s orbital. Where n is 2, the s and p orbital are possible. S hold up to 2, p hold up to 6 electrons. Where n is 3, s consists of 2 as well. So remember that s is always 2, p is always 6, and d can hold up to 10. You can also have where n is equal to 4. You basically will have the same thing. You will have S, T, D, F. And with F, 14 electrons are possible. So as you increase in increments, you basically add 4 electrons. So P would be 6. D would be 10. But what's important for here is that the orbital or the valence electron has a configuration of P with 5 electrons in all of these. According to the quantum mechanical model of structure of atoms, the electron in an atom can be described as occupying a particular orbital. To try to understand the chemical behavior of atoms of different elements, how many electrons can occupy an orbital? And we already know this, right? So the spin quantum number indicates the orientation of the spin. The electron can either spin up or it can spin down. So where ms is positive half or 1/2, the spin is up. Where it's negative half, the spin is down. So this part of the configuration actually relates to the atoms, the ability of the atoms to move in opposite direction. So remember that with the s orbital, you have 2 or a maximum of 2 electrons on each. And for the other orbitals, you can have up to 6. The atoms cannot spin in the same direction. It's a matter of opposite effect. So one would spin up, one would spin down, one would spin left, right, for example. The electromagnetic connection has to be opposite in order for the electrons to be contained within the orbital. So when placed in a strong magnetic field, like those using magnetic resonance imaging or MRI, electrons behave like tiny magnets. When the electric charge move in loops, they create magnetic fields. So the scientists postulated that electrons which are negatively charged must be spinning. So electron aligned to the magnetic field, ms plus half, them spin up. The electron aligned against the magnetic field spin down. They can't be moving in the same direction, especially if they're on the opposite side of the orbital, because that would mean that they would have a tendency to collide if there wasn't any law controlling the angular direction of each electron. Because our modern model describes the electron as deionized wave, the spinning particle is no longer considered literally correct, but the magnetic properties of the electron are consistent with notion that they are spinning in one or two directions, and we often refer to the electrons as being either spin up or spin down. We use the quantum number ms to distinguish between the two possible spins, and so it can assume only two possible values. So it's either plus 1/2 or minus 1/2. Using this quantum number now, for nitrogen in the s orbital, one would spin up, one would spin down. In the 2s orbital, one would spin up, one would spin down. For the 2p orbital, remember that the last 3 electrons in the p orbital singly occupy this orbital and they have the same spin. The nitrogen is atomic number 7 because when 1s2 are possible, they have to have opposite spins. In 2s, 2 electrons are possible, they also have to have opposite spin. In 2p, up to 6 electrons are possible, and we only have 3, so all 3 have the same spin. For oxygen with an atomic number of 8, the 1s orbital is fully occupied, so both electrons spin in opposite direction. 2s is the same. For 2p, we can occupy up to 6, and in this case we have 4, so 2 will have an opposite spin. With the introduction of the spin quantum number, we also need an additional restriction. The Pauli exclusion criteria states that no 2 electrons in an atom may have the same set of quantum number. This is the wave equation of saying that 2 particles cannot occupy the same space. So they should not occupy the same space, they can't collide, they should not have the same spin. They also have to be anti-parallel. Only 2 electrons can occupy a given orbital. The 2 electrons have opposite anti-parallel spin. The major consequence of this principle is that no more than 2 electrons can occupy any orbital. If 2 electrons occupy the same orbital, they must be spin paired, one with spin up and the other with spin down. Now that we know that orbitals can hold 2 electrons, how do we know which orbitals in a given atom are occupied? No 2 electron in an atom can have the same 4 quantum number. So this is because when they are in the same orbital, the value of n, l, and m, l are the same. Therefore, they must be opposite spin with different ms number. So they don't have all 4 quantum numbers the same. We already noted that in the ground state of an atom, electrons will occupy the lowest energy orbitals available. But how do we know which orbitals are lower in energy and what causes them to be lower? First, realize that a negatively charged electron is attracted to a positively charged nucleus. So we have the ground state, the excited state. The atom become excited when they absorb energy from the outer source, or relaxation occur as a result of emission of excess energy as radiation. The electron in smaller orbitals are held more tightly to the nucleus, so they have lower energies. The size of the orbitals tend to increase as the number of n increases. Putting these two ideas together, we conclude that the energy of atomic orbitals will increase as the value of n quantum number increases. The energy decreases the closer the electron is to the nucleus. The energy increases the further away the electron is from the nucleus. For hydrogen atoms, this is the entire story because most of the electron configuration and energy levels were only studied by using hydrogen. But for multi-electron atoms, we must think about the interaction further. The first difference is the size of the nuclear charge. It will be larger for other elements than for hydrogen. Larger nuclear charge exerts stronger attractive force on the electron, so the size of the orbitals will tend to decrease for higher atomic numbers. orbitals. More importantly, the electron in the orbitals interact with other electrons and not only with the positively charged nucleus. Force of other electrons are also affecting the electrons collectively. So not only the positive charge on the nucleus, but also the charge on other electrons. Even though it might be considered insignificant, collectively, all the electrons have an attractive force or an influence on the charge of the individual electrons. The attractive force goes for electrons in larger orbits, and the charge they feel is some combination of actual nuclear charge and the offsetting charge of electrons located in smaller orbital closer to the nucleus. So they kind of feel the charge. So the charge of the electrons that are being pulled towards the nucleus also have an effect on the electrons collectively. The masking of the nuclear charge by other electrons is referred to as shielding. Instead of interacting with the full nuclear charge, the electrons in the multi-electron atoms interact with an effective nuclear charge that is smaller than the full charge because of shielding effect. So here we can see the electrons that are closer to the nucleus are attracted towards the positively charged nucleus, while the outer electrons are also attracted to the nucleus, but there's also a repulsive effect between the electrons that are at different energy levels, and as a result create a nuclear charge or a shielding effect. This marks the end of part 2. This will also be followed by part 3. Hopefully this was informative, and I'll see you for the next lecture.